A magnet can have the perfect shape, the right metal, and even a shiny coating, and still not be magnetic. That is the strange part. A factory does not simply cut metal into a ring, a block, or a tiny disc and call it a magnet. It has to mine the material, purify it, melt it, crush it into powder, force that powder into alignment, bake it into a solid, protect it, and finally hit it with a magnetic pulse. Only then does a dead piece of metal become something that can pull, hold, spin, vibrate, or move the machines around us. That is the hidden process behind how magnets are made. The real trick is not the shape, it is invisible order inside the metal. A magnet works because tiny internal regions are forced to point in the same direction, like a crowd suddenly marching together instead of wandering around. When they point randomly, their forces cancel out. When they line up, the pull becomes strong enough to feel. That is why a tiny piece can hold your grocery list, drive a speaker, spin a motor, or help an MRI scan a human body. Most of us meet magnets in the least dramatic place possible, the refrigerator door. Behind that little click is a chain of mines, acids, furnaces, tools, coatings, and electric pulses. The wrong assumption is that a magnet is just a special kind of iron. Cheap fridge magnets are often ferrite, made from iron oxide mixed with barium or strontium compounds. The tiny monsters inside phones, headphones, tools, and electric motors are often neodymium magnets. They are usually made from neodymium, iron, and boron. But purity alone is not enough. The factory still has to solve a stranger problem: direction. The ingredients must become an alloy, powder, a pressed form, a heat-treated solid, a protected part, and only at the end, a magnet. Miss the direction step, and the object may look finished, but behave like a lazy paperweight. In magnet making, looking done is not the same as being alive. That is why the final factory step matters more than the shiny surface. For the strongest magnets, the story begins far from the factory floor, inside rare earth ore pulled from open-pit mines. Neodymium is called a rare earth element, but the name is a little misleading. It is not rare like a diamond in a movie vault. It is rare in the annoying way, scattered through minerals and mixed with elements that behave almost the same. And this is where the expensive part begins. The rock is drilled, blasted, hauled, crushed, and ground until valuable minerals are exposed. Then chemistry takes over. Acid treatment can dissolve rare earth elements into a liquid solution. Inside that liquid, neodymium swims with chemical relatives that are frustratingly similar. Separating them is like trying to sort a bucket of nearly identical keys in the dark. The factory pulls one chemical cousin away from another until neodymium is clean enough to use. At the magnet plant, the ingredients are weighed carefully. For a neodymium iron-boron magnet, the idea is simple. Neodymium brings strength, iron carries structure, and boron helps stabilize it. Simple, however, does not mean forgiving. Neodymium reacts easily with oxygen, so factories use vacuum furnaces to keep air away from the batch. In some processes, the molten alloy is rapidly cooled into thin flakes. That sudden cooling is not just for speed. It controls the alloy structure before the material is crushed into fine powder. Now comes the step that decides whether the future magnet becomes ordinary or extremely powerful. The powder stage matters because every grain behaves like a tiny compass needle. If the grains point randomly, their forces fight each other. This is where shape stops mattering and direction becomes everything. The powder enters a mold and is pressed while a strong magnetic field runs through it. The field tells particles which way to face before the material becomes stubborn. Think of it like combing wet hair before it dries. Then, the pressed piece enters a furnace for sintering. Sintering bakes powder grains into one hard piece without destroying the direction the factory just created. It bonds the grains so the part can survive machining and real use. Neodymium magnets are powerful, yet they can behave more like ceramic than steel. Drop one, and it can chip or shatter. That danger is not a side story. It changes how factories cut, handle, and package the parts. That is why cutting and grinding must be precise. Shape still matters, just not in the way most people think. A motor may need curved segments. A speaker may need rings. A sensor may need blocks. A toy may only need a cheap strip that barely tries. After shaping, many neodymium magnets need a protective coating, often nickel. Neodymium iron boron can corrode when exposed, weakening performance or destroying the part. So the factory gives it a protective skin before the final moment. And here is the trick most people never see. The object has survived mining, chemistry, melting, cooling, powdering, pressing, baking, cutting, and coating. Yet it may still not be fully magnetized. To wake it up, the factory places it inside a magnetizing coil. For a fraction of a second, the coil creates a field so intense that internal domains snap into their final direction. Because countless tiny regions inside the material stop arguing and start pulling together. That is why every step is really about control. Control the chemistry, control the grain size, control the direction, control the heat, control the surface, control the final pulse. Ferrite magnets follow a related but cheaper path. Instead of rare earth metals, factories mix iron oxide with barium or strontium compounds, press the powder, and fire it. It is inexpensive, resists corrosion, and handles heat well. That is why fridge magnets and motor magnets may come from different families. The other wins when power must fit into a tiny space. The hidden process behind modern life is really a trade-off machine. A cheap magnet and a high-performance magnet are not trying to solve the same problem. Factories are not only asking how strong it can be, they ask how small, cheap, heat-resistant, precise, safe, and durable it must be. That decision shapes everything from raw material to final pulse. It also explains why magnets are everywhere without feeling special. They are buried inside motors, speakers, sensors, generators, hard drives, scanners, vibration units, and camera stabilizers. The stronger they became, the smaller our machines could become. That is why magnets helped shrink modern life. A speaker, drill, car motor, and phone camera all rely on the same idea. Control the material inside, and you control the force outside. So next time a cheap magnet snaps onto your refrigerator, remember what it is. A magnet does not get its power from its shape. It gets it from invisible order, forced into metal.